The following is a presentation of the Six Arrows Radio Network.
Today on the Workbench, we talk about designing your own printed circuit boards. Stay tuned. Welcome to the Workbench. I'm your host, George, KJ6VU.
And I'm Jeremy, KF7IJZ.
The Workbench is sponsored by CADsoft, makers of Eagle PCB design tools. Get your free copy at cadsoft.io. And by MCM Electronics, where I can and you can buy all of your electronic parts needs and equipment. Check out mcmelectronics.com today.
Welcome back to the Ham Radio 360 Workbench podcast. Good evening, Jeremy.
Holy cow, you're here.
Yes, I am back.
You're back from special assignment to parts unknown.
Yeah, it was a long trip, but good. So the point of the show is to talk about how PCBs are designed and made, and encourage people, if they're going to do their own electronic circuit design, to consider doing their own boards, because it's relatively inexpensive and certainly much easier than it used to be in the past. So why not?
Now, before we get into that, we're at episode 10.
Yeah.
We have been talking about our own project that had a design PCB. Why don't we tell our listeners how they can get themselves a Ham Radio 360 Workbench K6B Easy and 10 analyzer?
That's a great idea. So we made some good progress over the last few weeks. We've finalized the board layout and sent the Gerbers off to the fabrication house, and we'll explain what that means later. But essentially, we're in the process. We've got boards that are being manufactured, and they should arrive here in the next week or two. So we'll have a set of blank circuit boards all ready to go.
Now, what we have been trying to do behind the scenes is we were looking at a lot of different options on getting the kit to you, our listeners. Everything from a fully parted out kit to having you source pieces individually. Now, if you remember, we asked for feedback from the audience several episodes again and got a ton of emails, like probably over 100. From folks saying, yes, I'm very much interested in this, but I really would like to keep the cost at $50 or less. And so we have made the conscious decision, rather than getting things kitted out, which would have put the price up closer to probably the $7,500 range, we are going to post links where you will be able to source all the components yourself. And George, what are some of the things we've done to make that pretty easy for folks?
So all the little stuff like resistors, capacitors, screws and nuts, all the really common stuff, we've made a shopping cart on DigiKey, and we'll have a link, and you click the link, your browser points to the DigiKey website, and up on the screen pops a list of a whole bunch of components. And all you have to do is say buy, and it's about that part of the bill of materials. Those components, all told, are about $20 plus shipping. And they're also pretty common commodity parts. So a lot of you guys will have these in a junk box because they're common value 10K resistors or a 440 screw and a nut, things like that. So you may well have a lot of those parts. So the common stuff will be available through DigiKey or supply it yourself. There's a couple of other more exotic parts like the digital synthesis module, the Arduino microprocessor board that we're using, things like that are a little bit more specialized. We'll give you links to go find those from various sites on the internet as well. So you'll have to go to maybe 4 or 5 places to get all the parts, but that will get the price down as low as possible.
Yes, it will. And then finally, the boards, and then one of the things that we were very lucky to be able to get our hands on is a bunch of new old stock germanium diodes, which are very important in the design. And you will be able to order the boards and the diodes directly from the Ham Radio 360 folks. And then, as we said, we'll have the links to everything else. A lot of this stuff is going to come from eBay. But there will be other alternatives. For instance, the Arduino that we used, SparkFun makes a version of the Arduino, which is the Arduino, what is it called? The Pro?
It's the Pro Micro 5-volt version.
And they sell that Arduino for like $20-25, but there is a clone of it available on eBay for like $350.
Well, close. It's $6, I think.
Sorry,
shipped.
$6 shipped.
Yeah. So we'll publish both of those links, and so you have a choice. You could either get it from the reliable vendor in the U.S., which is SparkFun, if you want to pay a bit more. Or if you want to go for the bargain basement version, you can buy it off of eBay, or not eBay, but an outfit called Deal Extreme. That's one of these electronic gadget cheap offshore sources. And I've played with the version of the controller from Deal Extreme, and it's perfectly fine. I have absolutely no problem with it. So if it were me, I'd probably get that one and try it. And if I had a problem with it, I could always go get the SparkFun version. But you'll have the choice. And to your point, Jeremy, there are a few things have to be purchased off eBay. So the synthesis module is available from several suppliers on eBay. And the LCD display, you can get those things anywhere, but by far the cheapest source is on eBay. But if you want to go to a known reputable source and you're willing to spend more money, you could do that as well.
And we will be posting a link again to a page with all the information as well as the instructions, the full bill of materials, etc. Because the nice thing about this is it's an open design. If you don't want to use the links that we provide and you want to source everything individually from your own suppliers, you're able to do that as well. And you will be able to find that at hamradio360.com, hamradio360.com/workbench, which is the page we have set up now that is an index of all the Workbench episodes. And we will make sure to put at the top of that page the link to this entire project page. On top of that, the Kale has installed on hamradio360.com a forum, and it will be under that forum that you will be able to ask questions and whatnot during the assembly, and that's where we're going to be able to field questions, comments, suggestions, etc. that come up as you are putting these together.
So that'll be a good resource because we'll be there. Barrick, who is the designer, will be there in the forum as well. We'll be able to support and answer questions for each other.
Does he know that?
No, but
he's a good guy.
He is. He'll know when he listens to this episode.
And on top of that, in the background, we are still exploring other options to have these things kitted out as much as possible. So that way, if you're willing to trade cost for convenience, that may be an option for you in the future. So if we have news on that front, we will let you know.
And ultimately, when we have all the documentation on the website, we'll also be posting the printed circuit board schematic and layout data files, not just a PDF, but the actual board layout tool files, so that if you want to play around with board layout tools yourself, you can download the source for the layout and use that to mess around with and maybe make a derivative version of the design, or just see how we did it.
And of course, the design files themselves will be released as the raw Eagle files, correct?
That's right. There's two files, one for the schematic and one for the layout, and it's in Eagle format.
Awesome. And on top of that, we will be doing an episode in the future that will cover the assembly of this thing, as well as a little bit of information on troubleshooting, etc. Haven't worked all the details out yet, but we may even try to incorporate video for that one, which would make a lot of sense.
Can you do one of those video things where you can speed it up so you can see the hour assembly done in like 2 minutes?
Well, of course, with the magic of the internet, you can do anything.
Awesome. That'd be pretty cool.
Yes, it would. Actually, I think it would be cool if we were to, try to, get online, synchronize these things, set a couple of cameras up to keep track of our workbenches as we're doing this, and then build them together and see who's the faster solderer.
Yeah, or better.
Well, that's going to be you.
I bet your soldering iron is going to be on and ready to go when you start assembly.
Yeah, it will be.
And if you're looking for an automatic shutoff design, I can point you in the right direction.
Yeah, check out episode 9.
So what's in the news? What's happening that you've picked up lately?
Well, I came across a new radio that I think is interesting, but I can't tell you how interesting I think it is.
That doesn't sound very interesting.
Well, there's a company out of Colorado. It's interesting thing number one, American company manufacturing in America. Mm-hmm. The company is called Com Radio. Com Radio hit the scene, 3-4 years ago, maybe. I think it was like 2013. They have this absolutely cute little desktop receiving radio called the CR. Now it's the 1A. And it basically covers DC to 440, except for the 6-meter band, because I guess that's where their IFs and stuff are is in the 50 megahertz range. But these radios they had DSP on board to do all kinds of crazy, really good filtering for receiving. They had built-in lithium batteries. And then the CR1A, which was the replacement of the CR1, there was a USB port, and you could get 192 kilohertz bandwidth of a spectrum out of the radio that you could look at with your, SDR software package of choice. Really cool, but probably not cool enough for like the $500 price tag. At one point, I think they were up to $600. I don't know where they're at today. But what's cool is the company has released or is going to be releasing a 10-watt QRP radio that will do 160 meters through 10 meters. And it's going to have the same electronics, the same filtering. Apparently, it'll do sideband CW, AM, and FM. I have no idea what the price is, which is why I said I don't know if it's as cool as it could be. Because if they come out with a very competitive price, I think it'll be great. Because these radios are pretty small. I don't know what to compare them to because I don't even know what size. I don't know what books look like anymore because I haven't bought a real one in a long time.
It looks like your iPad.
Oh, yeah. Okay. Yeah. So this thing is about 2/3 the size of my iPad mini if you stack like 3 of them up together. Anyway, it's a cool looking little radio, and their stuff was pretty decent quality. So that it's interesting to see, though, another QRP radio enter the fray.
I'm taking a look at it on the Universal Radio webpage. I had never heard of this thing before. It looks pretty nice.
Yeah, like I said, the old one was the CR1A. A friend of mine bought one as a receiving radio. The thing that kept me from I came very close to buying one several times because especially, if I was out at a park or traveling or something, you just put a long wire in it and you have a really good HF receiver. That could also do 2 meter and 440. But I could never wrap my head around the fact that you didn't get 6 meters. Because one of the things I thought would actually be really cool, a good use case for this, is because it's so tiny and power efficient. Just leave it running on a beacon frequency for 6 meters, and if you ever had an opening happen, you would know pretty instantly. But
yeah, that's a good idea.
It wouldn't have worked because it doesn't receive in 50 megahertz.
Yep. That's a good point. So is this really an SDR or is this a conventional radio inside?
Well, the fact that it gives you what I'm assuming is quadrature data out. This is when we did the SDR episode on Ham Radio 360. That was one of the things that what really defines a software-defined radio. I assume, there's a big old fat DSP in there. And it's doing, I don't know if it's doing direct sampling or not. The fact that there is something blocking out the 50 megahertz tells me it's probably not direct sampling. But all the processing, all the filtering, all of that's happening on a DSP. And so I don't know. It may just be giving you an IF output over the USB. So I'm not sure.
Well, you'll have to get one so we can find out.
Well, that's pretty low on my list of purchases. I still have not, just in case anybody cares, I still have not gotten my that Kenwood or the ICOM. Although I do want to mention, I think Kenwood has been doing a pretty phenomenal job with firmware updates. They've already released version 1.04, just came out at the end of October, so about a week ago. And one of the big issues that have been happening was GPS data was not getting from the Kenwood THD74 to other ICOM radios correctly, or even getting on, through like APRS.FI using the DPRS-A mode. But the firmware update that they just released, as I understand, at least now your GPS data will show up on other ICOM radios. So that's a step in the right direction, but it shows that they are very interested, and they have been releasing firmware updates pretty quickly, and I really am happy to see that. I think that's possibly a lot due to the fact that Don Arnold, W6 GPS, who, if you've ever done any APRS stuff, you've seen his videos on YouTube. But I think he's been really involved with the community, and this is his first foray into D-Star. And I think that, because he has a relationship with Kenwood, he may be, I don't want to say influencing, but I think helping get some of that feedback into their engineers' hands to address fairly quickly.
Very good.
Well, I think that's just speculation.
I think putting out a radio, their first D-Star radio, they're probably going to make a decent radio, but there's probably things missing. And I think if they do keep on the track of putting out more firmware updates with more features, then I think they could build quite a little following.
I do too. I really look forward to, because, if they make the mobile, especially in today's world, well, all the brains of the thing can translate over to, they make the handheld. All the brains can translate over to a mobile. The only difference is you have a more powerful RF deck. Mm-hmm. So I really look forward to them, nailing out some of the bugs on this thing and then moving into a mobile format in the future.
Well, that'll be interesting to see where that goes. Thanks for the pointer on that. I never heard of these guys before.
All right. So, George, what's on your workbench this week?
So I've been traveling as we talked, and so I haven't had too much bench time, but I have been playing around with a couple of projects. I picked up one of these little low-power transceiver boards from Hobby PC. So this thing is a RS-UV3. It's a little printed circuit board about 2.5 by about 4 inches. And it's an FM transceiver, 3 bands, 2 meters, 220 and 440, puts out 200 milliwatts, and you control the thing through the serial port. So there's no display, there's no keyboard, it's just a circuit board with a power jack and an antenna jack and a serial jack and a speaker mic jack. So I guess the idea behind this radio is that you could use it for various projects where you need a low-power RF deck and receiver. So, for example, you could build a APRS digipeater out of it, or a conventional packet radio, or what I wanted to do with this thing is build a little baby low-power repeater. And rather than using commercial radios, which I normally do, I wanted something very small. So I get 2 of these things, and I'm going to wire them up to a little repeater controller I'm building, and use this as the RF deck. Now, you can go out and buy a handheld Bofang for half the price that puts out a lot more power. But if you want to do more of a hacky project, this is great because they have a microcontroller. You can talk to the microcontroller through the serial port and tell it the frequency, the mode, the offset, the PL tone, all that sort of stuff. So for a platform to control, it's pretty slick. So we'll see.
So in looking at this, I noticed that there are unpopulated headers that make this Arduino Shield compatible, so you can plug an Arduino into it. Now, I have a question. Mm-hmm. So, at the end of the day, there's a radio. Obviously, there's an analog signal path because, like you said, there you can set the PL tone and all that stuff. You can plug a mic and a speaker into it. But I wonder what the modulation type is, because with this thing just having a serial input, there has to be a modem on board to modulate the data into RF. And so I wonder if it's like straight AX25.
Oh, no. There's no data at all. It's a FM transceiver. So the heart of this thing is a single chip. And it's I don't have the documentation up in front of me, but there's a single part that's the transceiver chip. And it's got the receiver and the transmitter. So it's if you kind of boiled it down to a block diagram, it's just like any conventional FM radio. So the receiver has antenna in, and there's some filters. There's some band pass. I think they're high pass filters. And then it goes into the chip and comes out as demodulated FM as a discriminator output. There's probably a little audio amp, because I think you can drive a speaker with it, well, either that or to an amplified speaker. So anyway, it's ultimately discriminator audio out, And then on the input, there's a mic jack. So there's a little mic amp, and that goes into the modulator and then multiplies up to the band, and out it goes to the antenna. So it's a conventional FM radio.
I just noticed that. So in other words, the serial is more for controlling the parameters, like what frequency it's tuned to, PL tones, things like that.
That's right. So exactly. So the heart of this thing is that RF chip, which is essentially a FM transceiver on a chip plus a microcontroller. And the microcontroller is just what you said, Jeremy. So there's a serial port that the user would get to, and then the microcontroller has probably a SPI or some other similar interface that controls the radio chip. And you don't have to think about that because it's supplied with firmware already built in to the microcontroller. So you can talk to the serial port, and there's an ASCII command set. So there's like 25 commands. Set the frequency to this, set the PL tone to that, set the offset to this, volume up, volume down, squelch open, squelch closed, whatever. So all that stuff is ASCII commands. And you could literally take a PC with a dumb terminal program, plug the serial port from the computer into this thing, and just type commands like 2 letters and a number, and it's like set the volume to that number, whatever that would be.
Yep, and I notice on the block diagram here that there's basically just line level audio output. And, you made the comment about being pre-discriminator, which, you in theory could use this for a hotspot if you did have another modem that output the quote-unquote, I'm using the word audio, but that's the wrong word, but you know what I mean.
Well, what you're really getting out is discriminator audio. Discriminator audio is essentially a analog waveform of the modulated signal. It's the baseband audio coming out of it. So if you wanted to, let's say, use this thing as a digipeater, for instance, then you'd have to have an APRS or TNC modem chip, or do that in software like with a Direwolf on a Raspberry Pi or something like that, where that sound card would just plug straight into this thing. The audio would plug into this thing. So this is essentially a little circuit board, low power transceiver. So you should think about it just like any other transceiver. And the user's interface, like a mic and speaker or a computer modem or whatever, would be plugged into the audio path of this thing.
So given that stuff runs through the discriminator, would I be correct in assuming your maximum, like if you were doing like APRS, like traditional AX25 packet, that you're limited to 1200 baud?
Well, if you use it as an audio signal source, yes. So when you look at the higher speed packet modems, the 9600 baud modems, they're usually they're not audio signals typically. Often they're using a different modulation scheme, like a GMSK or some other kind of modulation. So I haven't looked at this close enough to know whether or not you could do that with this thing. For sure, you could use a 1200 baud audio modem, no problem. But whether or not you could do a higher speed 9600, I don't know.
Okay.
Probably.
Still pretty cool.
Yeah. Well, so for my application, like I said, I wanted this low power FM receiver transmitter board pair because I'm doing this little baby repeater controller project. So I wanted something very small, lightweight, and portable. It would actually be cheaper and better to go out and buy something like a used Motorola mobile radio. For the price of this thing, you could buy a 40-watt Motorola mobile radio, but it's significantly bigger, takes a lot more power, and is much heavier. So for a little development board pair, this is pretty cute. But for a real installation, better radio would be cheaper per watt.
Well, cool.
Yeah. So anyway, so this sort of dovetails into the second half of the project, this little repeater controller thing. So, John KJ6K and I have designed a repeater controller some years ago, and those are used pretty widely in linked repeater systems. And for that project, we set the feature set knob to max and ignored the price and hit the button and made a very fancy repeater controller. And they work great. But sometimes you want something that's really inexpensive and simple. And so I've been tinkering around with a much simpler design and looking at some of the new chips that are available to make it smaller and cheaper, and potentially might even make it an open source project. So we may do that. Maybe that'll become a Workbench project at some point. But
that'd be cool.
Yeah, it could be. And so I've been messing with some new chips. A bunch of the peripheral chips these days you can get are controlled through a serial bus called I2C or I2C. And so I've been messing with some of those chips. There's a I/O expander and a real-time clock and some other stuff. So I'm trying to figure out how to make all that work and maybe come up with this low-cost repeater controller.
And they say hams don't build anything anymore.
Yeah, well, the funny thing is, a lot of times I find what I want doesn't exist. So that sort of forces me to go try to figure out how to make one. So that's sort of the motivation anyway. So that's what's been on the bench. And if that stuff makes some good progress, I'll let you know.
Well, it's funny that you mentioned about the things you want don't exist, because that actually kind of ties into what I've had on the bench since we were last together.
What's that?
So I was camping last weekend. I knew CQ Worldwide was going on, but I also knew that I didn't. Band conditions were terrible, and so I thought about taking the KX3 and my Pac-10 Mini out. Ultimately, didn't want to fool with it, and I was still really excited about the little BlueStack micro that I have with the DV Mega Hotspot getup. And so I was like, you know what, I'm going to take that with me camping, because where I was going had good enough cell service, and I'll play radio by trying to just hop on a few different D-Star reflectors. But the problem is this thing is just two circuit boards put together. I don't even have the right size screws to actually physically attach them together. There are a couple of cases, both of which are 3D printed, available. The source where I bought my board from was selling these cases for $18. Well, I have a 3D printer, and $18 is, for somebody who owns a 3D printer, a little steep. So I actually sat down and started designing a case to hold these two things that would give you visibility to the LEDs. It would give you the ability to attach a fairly thick antenna to the SMA connector. It would have a port for the USB connector and a window to be able to push the wireless versus wired mode selector on the board itself. So I sat down and using Autodesk's Fusion 360, which if you remember Matt from the previous episode, I think this is one of the things that he has oversight over. It's a very powerful program that has only gotten better since I started using it about a year ago. The thing I like about it is that you literally start off by drawing two-dimensional sketches, and then you flip over into a 3D view, and you can start extruding and collapsing the different geometry. So if you draw like a square within a square, you can then just extrude that square. And the approach for the case I took is much different than the other one that's available commercially, which is two halves that snap onto one another. Whereas I built one that was all one piece with two channels to slide the PCB in, and then a little door that slides over it. But it took me 5 iterations of printing this thing out, and the 5th one is pretty much perfect. And I actually will be signing up for an account on either Umagine or Thingiverse and making the STL files available for free, so anybody can print one of these. But it was really satisfying to get that done.
Sounds very nice.
Yes. And it was nice to do because it was a refresher. I hadn't had to design anything in a while. And like I said, Fusion 360 has changed since I started using it. It's actually gotten easier to use. There's still a few things about it that I still don't understand why it does some of the things it does. But I can muddle through it. I mean, in the grand scheme of things, I probably only have, I don't know, maybe 3 to 4 hours conservatively, or maybe liberally, into designing this case, between, getting the calipers out, getting my initial measurements, printing the first one, then doing a test fit, and then doing all the measurements for adjustments. For the actual design time, not the print time, probably about 4 hours total into getting it pretty much perfect. In fact, there's a couple small adjustments I want to make that I think would just make it that much better. But I mean, it's completely functional as is. Took it with me camping. It was perfect. It kept the boards protected. I was able to get on D-Star while I was camping, which that was fun. So yeah.
Awesome. So when you're doing that, did you connect onto your cell phone through the Wi-Fi, or how did you connect?
So yeah, that's actually that's the convoluted part. So I'm an iPhone user. I'm not an Android user. And they claim that there's going to be an iPhone app for this, but I don't know that there ever will be, because I don't know if they're using full Bluetooth or Bluetooth Low Energy. I haven't been able to get that question answered. If it's full Bluetooth, then I think it's an arm and a leg if you want to talk to an Apple device with full Bluetooth through an app in the App Store. So there's an Android app that's free. There's also a Windows app. And this board can operate either via Bluetooth or plugged in via a USB to serial bridge that's on the actual board. So the way I have this set up, I own one Android device, and it's a tablet. It's the second generation Nexus 7 tablet. So I take the tablet, I connect to my phone as a hotspot for over Wi-Fi. And then the tablet was connected via Bluetooth to the BlueStack, which was just plugged into a little travel, like an Anker USB battery. And then the D-Star radio, of course, was wireless, and that was it. There were actually 3 wireless links involved. So D-Star UHF to the DV Mega, then the BlueStack to the Android tablet over Bluetooth, and then the Android tablet to the internet over Wi-Fi.
And it all works well.
Yeah, surprisingly. I had a long QSO with Ed W4EDF using that exact same setup. I've actually used it in my car, even mobile.
Oh, very cool. So I do a mobile hotspot, not with that board set, with just a DVAP and a Raspberry Pi. And it works great. I find that it's really handy when you're traveling somewhere and you just don't have the time or the energy to outfit your car with a bunch of portable ham radio stuff. If you just bring your D-Star HT and the little shoebox of your hotspot, then you're kind of good to go.
There's one major difference between these two approaches. Well, there's 2 major differences. The first of which is that the DV Mega and Blue with the Blue DV board will do D-Star, DMR, and Yaesu System Fusion. But the thing that's actually interesting is with the DV, or sorry, with the DVAP, the DV access point, you still have to set all of the 4 call signs in your radio. You're still controlling what reflectors you're linked to in your radio. If you want to use any of the alternative or foreign reflector sets beyond the REFs, if you wanted to use like the X reflectors or the DCS reflectors, you have to configure that in the software running on whatever the host machine is. What's kind of cool about the Blue DV stuff, and if you're not interested in learning about D-Star to this intimate, all you do is set CQ, 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 and then your call sign. You use repeater 1 or repeater 2, stay empty. And what you connect to via D-Star is actually set in the software, not from your radio.
From the Android software?
Yeah. So like when you go into D-Star mode, you don't say D-Star, you pick REF, and then there's a drop down with all the reflector base numbers and then all the nodes, A through E or whatever.
Okay. Well, I can see where that, I think that there's pros and cons to both. In one way, having the access point just be a brick is convenient because then you just do everything from the radio. But it's probably easier to make changes to the thing on the Android tablet if you wanted to do something that's not programmed in your radio, I guess.
Yep, especially if you have an older ICOM handheld. Now, again, for DMR,
yeah, fair enough.
For DMR, you're still relying on the radio to set what talk group you're connecting to, through the contacts, but. And then System Fusion, there were different. Again, I'm not familiar with Fusion at all. I noticed there were a bunch of different rooms, or again, I don't know if they're called reflectors or bridges. I don't know what they call them, but you could select that in the software. But still pretty cool and a neat little pairing, especially if you're able to get one of those at Dayton for a good deal. Although the prices on the DV Megas have come down, you can get a mono band 440 megahertz one now for like $130 from HRO or Gigaparts.
Mm-hmm.
And then I got the the Blue DV board. The American distributor I found was Grapevine Amateur Radio, and it was like $45. So all in, still cheaper than a DVAP by quite a bit.
So did you, when you made the case, is it a one piece or is it like a clamshell, or how did you make that?
So the bulk of it is a single piece that basically, I designed it so there are two channels for the edges of the board to slide through, which you have to be careful because on the DV Mega, some of the components, the surface mount components, are like right up on the edge. So I had to build gaps in and things. So anyway, you slide the board in into this single piece clamshell, and then I built a door that has a channel that it slides in to kind of lock it in place. Whereas the commercial one you can buy is a top and a bottom half that you actually snap together and then can screw together. This was, a little bit more quick and dirty, but as long as you're not out there like grabbing it by the USB cable and tossing it around, the door doesn't really slide out. Like I intentionally made the door just a tiny bit tighter so that it wouldn't just like fall out of the channel.
Yeah, nice.
Yeah, I like I said, I'll get that posted and send links out to that to folks.
So if you had those files and wanted to go print it, and you didn't have a 3D printer, I assume that there are services you could find somewhere, and you send the files, and then they'll print it for you.
Yes, in fact, there are. There's a couple that come to mind immediately. They're probably some of the older ones in this space. There's a company called Shapeways, Shapeways, and then there's another one called 3D Hubs, where you can find basically people like me who own 3D printers that can take jobs and can bid on jobs. In a future episode, as we were talking about designing a case for the antenna analyzer, I had a ham who is down in, I believe, Alabama, reach out to me and said he would be interested in help, if I needed help designing it, or, he actually runs a business that does 3D printing. And he's a ham and he's a listener of the show. And we might actually have him on in the future to do an introduction to 3D printing with us for our listeners. So I'll make sure to put his information in the show notes.
I thought the 3D printing was kind of a cool idea. I just didn't really see myself getting into it. But, the more I talk to you about it, the more I can see applications for it where there would be a project like this where you have a little circuit board. In fact, maybe this little hobby PC thing, make a little box for that, because I'm going to stack two of these circuit boards, one on top of each other, so it probably wouldn't fit their standard case. But it might be kind of fun to do a little 3D printed box for that.
It is one of the most powerful technology. When I first got this thing last year, and I have a fairly small and entry level printer. It's my printer out of the box could only print 4 inches by 4 inches by 5 inches, but the printer was $400. I learned a ton about 3D printing, how to troubleshoot prints, how to actually work on these things. There was an upgrade kit available that would make it 4 inches by 8 inches by 5 inches and then all told, I'm out $475 at that point. I actually, when you run a heated bed on it, that requires a high power supply. So I actually took the power connector from the printer and terminated to Anderson power poles and use a ham radio power supply for it. For my daughter for Halloween was Hermione Granger from Harry Potter. I 3D printed her a wand. I've made her a lot of toys over there, but there was a Raspberry Pi cluster thing I did last year, which was when I first started using Autodesk Fusion 360. And it is just so powerful to have an idea, sit down, sketch something out, print prototypes. And I mean, the materials that I'm using, which PLA is polylactic acid, it's a fairly brittle but easy to work with plastic. And there are millions of material. Well, not millions. There's tens of materials that you can print at home for this type of printer. And like I said, we will do an intro to 3D printing episode, because this thing is truly one of the most important things I've ever bought in my life.
So if you were going to go out and buy a decent 3D printer now, like how much would you have to spend?
Truthfully, I'm fine recommending what I went with, which is a PrinterBot Play, which like I said starts at $400. Although I noticed monoprice. I saw something today. There was a monoprice printer for $167 on jet.com if you used a coupon code. It prints 4.5 by 4.5 by 4.5. There are some things about the design, and that's the thing. Like, there's a lot of nuances to how these things are designed that will determine print quality. But then they had another machine that was like 7.5 cubed for like $250 that gets fairly good reviews. But I mean, the price ranges of these things, they're determined by how big the build area is, whether or not there's a heated build platform, how high quality are the drive belts and the screws that are moving things, the motors, the control boards, the overall construction and rigidity. I mean, there's a million variables that go into these, and pricing isn't necessarily a good predictor of quality. 3D Hubs actually publishes a list every year of the most popular printers. They do a lot of surveys of all their users, so they get thousands of responses. So I'll take a note to include that in the show notes as well. But I can recommend the PrinterBot Play as a good starting point for a first printer. The thing that if you take, my wife talked me into doing this because $400 was affordable. If I didn't like it, I could probably still sell the printer for $300. That wasn't out a ton of money versus me, who tends to go all in on a hobby and then possibly loses money if you're not interested. But $400 for this thing, and as we're getting closer to the holidays, they'll have deals for 10 or 15% off. If it's something you're interested in, it's a no-brainer. But the first thing you'll get frustrated with is not having a big enough build area.
Mm. So you said $400, so probably $400 as an entry price, but I'm sure you could double that if you really wanted the fancy version, right?
You could, yeah. I mean, for desktop home printers, you get anywhere from $150 all the way up to like $4,000.
Wow. Yeah, well, let's definitely talk about that. I'd love to learn more about it, and I've got like 20 questions in my mind about the resolution and the speed and all that stuff. So yeah, that'd be really interesting.
All right. Well, I say at this point we should shift topics and get into our PCB discussion, because I have a project that I'm going to need some help on getting started with. But before we do that, remember that you can save 5% on your order from MCM Electronics, your source for everything component, Arduino, Raspberry Pi, microcontrollers. They have a bunch of things, all kinds of stuff like television remote controls and all of your audio video cabling needs. And everything you need to outfit your workbench is available at www.mcmelectronics.com. And again, you can save 5% on your order by using the code RADIO5.
And we'll be right back after this.
The Workbench is sponsored by our friends at CADSoft. They're the makers of the Eagle PCB design software, the very software George used to design the Pactena Classic, Pactena Mini, what him and Barrick are using to create this new antenna analyzer project for you here on the Workbench. They got hundreds of parts libraries, tons of reference designs, and a monster huge user community. Eagle's a great choice for your next ham radio project, and you can get your free copy of their software today. Click on over to cadsoft.io and start getting your project put together today.
So, George, a couple episodes ago, I got really excited and thought I could go off and be a big-time PCB designer. And I had told you I'd come across a chip from Linear Technologies that was basically like a 2-amp solar charge controller on chip. And in the data sheet, they give you a reference design, and they tell you by switching out certain analog components, you can control certain parameters of the charging algorithms, etc. And I was like, this chip looks awesome. And I was like, I'm going to go develop something. And then I was like, oh, wait, it's not quite that easy.
Well, it's not that bad, really.
Well, if Nick can figure it out.
Yeah, but he's a smart guy.
Yeah, I know. But I realized like the process of this, even though effectively I have a chip, I can order the chip. It's inexpensive. Mm-hmm. I have an entire reference design, so I don't even have to know anything about electronics. This is like the tracing of electronics world. Like I'm using somebody else's design, but I still couldn't quite figure out how do I go from, I installed Eagle,
mm-hmm.
but I think it would be good to have a guided tour of the design of hobbyist PCB design and layout.
Yeah, that'd be great. Let's do that.
Yeah.
And it's really not that bad, but it's like a lot of things that are a little complicated that you have to put some work in setting things up first. And once you have things set up, then it's pretty easy to do a bunch of things, a bunch of designs going forward. So the trick is really getting yourself kind of organized and setting stuff up.
So to start at the very basic level, we keep talking about PCBs, and a PCB is a printed circuit board.
Right. So a PCB is essentially a replacement for the old point-to-point wiring. So if you go back and look like at radios 50 years ago, you open them up and there's a bunch of, let's say, tube sockets and components, and they're all hand-wired, and there's a ton of wires between all the different devices. And the printed circuit board was a modern way to make circuits denser, to make them cheaper, and make them more reliable, and certainly make it much less expensive to manufacture. So the whole idea is that you can print the traces, which is essentially the wires, onto an insulating material and create a printed circuit board that is also used to hold the components in place.
Sounds reasonable.
Yeah, and there's lots of different alternatives. I mean, if you're a hobbyist of any sort, and you're building electronics, there's lots of different assembly techniques you could use. So tonight we're going to talk about how do you do a custom circuit board, but there's many other ways. And in fact, for most of my ham radio time in doing build projects, I would hand wire things. And so there are many techniques like vector board, and vector board was made by Vector Company, and it's a piece of circuit board material that's got a bunch of holes, and you would stick the parts through the holes, and then you would hand wire or solder little jumper wires between the components. And there's all kinds of little gadgets that they made to make that wiring easier. But at the end of the day, you would hand assemble this board and you would have one. So, and it may work or it may be a pain in the neck to debug, but that would be your board. In the old days, also for digital circuits, wire wrap was really popular, which is having a bunch of sockets, again, through holes on a circuit board and have these long posts sticking out. And you would take these very thin, like 28, 30 gauge wires and spin them around the post, wrap it around the post, and you would wrap it on either end of the wire on two different posts, and that would make the connection. So there's lots of different techniques over the years to make essentially a wired board of components. But so much has changed in the board world with the price of software coming down and the availability of low-cost fabrication services to make them, that it's really become practical for us to make our projects on a custom circuit board, even if we're only going to make one or maybe a couple.
Okay, so I'm sold. Where do we start?
Yeah, so good question. So the place to start is to pick a piece of software, because that's really the core, the tool that you're going to use. And of course, Eagle's a sponsor of this podcast, so we're going to talk about Eagle, but not because they're a sponsor. We're going to talk about them because it's widely used in the hobbyist world. So in ham radio or in any of the maker technical kinds of hobbies, there's some very popular circuit board tools. So commercial tools available are things like Eagle from CADSoft, that's now a part of Autodesk. There's other tools from companies like Altium or free software. There's a tool called KiCad that's available. So there's both free tools and there's tools that you buy. And then there's also tools that are made by fabrication companies that only can be used to manufacture boards through their services, and those are always free. So there's a lot of options out there. Personally, I picked Eagle because I wanted something that was pretty good in terms of features and had a lot of libraries of components. And the secret to making PCB design fairly easy is making sure that the parts that you want to use already exist in a component library. And we could talk in more detail about what that even means.
So you talked about having the features that you wanted to be able to use. So like for somebody who's completely new like me, and I'm literally, remember, I'm starting from, I have a data sheet that has a schematic in it, and I can read the schematic, but where do I go from there?
Okay, so let's talk about the overall process of making a circuit board, and then we could talk about some of that in a little more detail. So the basic idea is that you want to ultimately, through the computer software, define where these components will be placed on a circuit board and how the various pads or connection points where you solder it, how they connect together. And the typical PCB design tool has two parts to it. It has a schematic editor and it has a layout editor. And normally these two pieces of software are either one program or they're linked together. And we'll talk about why there's a linkage there. But the schematic editor is obviously it's a graphic design tool. It's a graphic editor. You bring up a blank sheet and you have a library of components and you pull the schematic symbols out of a library and you place them on the screen, and then you hook the pins of those components together to create the schematic. Now
does that include like micros and passive components and pretty much anything?
Yeah, exactly. So if you look at a tool like Eagle, for instance, if you just install Eagle and look at the libraries, there's probably 100 libraries of components that are installed with Eagle. And in each one of those libraries, there's anywhere from a couple of parts to maybe 100 components. So for instance, for passive devices, there's resistors and capacitors and inductors. There's connectors. There's transistors, integrated circuits. You name it. Everything that goes on that circuit board, there would be a library component for. And in the library, there's two views of that part. There's the schematic symbol, and there is the physical, what's called the footprint. It's the pads and the holes that are the mechanical aspect of that part. So let's take, for example, a resistor. I'm going to use a 1/4 watt carbon composition 5% resistor. The garden variety part you can get at any part store. That, let's say 10K resistor, I would start by going to my library and picking a symbol for a resistor and then dropping that on the schematic diagram editor. When I go to pick that resistor, there are different kinds of resistors. There's surface mount and through hole. There's small ones, medium ones, and big ones. And so you got to pick the right size resistor that you want to use on your circuit. And once you put that symbol on the schematic, that's the first step. When I put a second component on that schematic, maybe a second resistor, then I need to wire those two things together. Now, there's a really important concept to wrap your head around, and that is that the schematic editor is not a drafting tool. So a drafting tool is simply drawing lines and squares and circles on a page that makes an image. That's while we do that in creating a schematic, what we're really doing is we're really defining how the components are wired together. So if I have two parts on the screen, like two resistors, when I draw a wire between those two resistors, not only does it look like those two resistors are hooked together graphically on the image, but in the database, it says resistor 1, pin 1, is now hooked to resistor 2, pin 1. So it understands the connectivity between those two pins. And that's a very important fundamental idea in doing board layout, is the notion that you're not just making a picture, you're actually defining electrically how the pins are going to be hooked together.
So this is an interesting thing to bring up, right? Because out of the box, I could take the schematic that is given to me in the data sheet, and I could duplicate it in Eagle. Mm-hmm. And based on what you're saying, I mean, it's not that you're just drawing the picture. You're telling the computer these things are electrically connected and they have certain relationships. But yet when I'm drawing the schematic, we're talking about where there's like a little squiggly line for a resistor, right? Or, mm-hmm. A triangle for a diode, things like that. Mm-hmm. And obviously when I see a printed circuit board, that's not what it looks like actually on the board. So when you're doing that, because I assume we're going to talk here in a minute about there's a difference between the schematic and then the actual how it's going to be on a board.
Right.
But when you're defining the schematic, is the program later going to use that when you're doing your design to make sure that you hook everything up together correctly?
Yes, it is. And that whole idea is a notion that is called correct by construction, which means that when you go to the physical design side, the second part where you're doing the board layout, you've already defined from the schematic what is electrically hooked up to what. And when you start your board layout, that tool knows what's supposed to be hooked together because of the wires that you've connected between pins in the schematic. So there are some tools out there that are very, very simple, that are essentially drafting tools, where the schematic is just a picture and then the layout is disconnected from the schematic. And when you go do the layout, you're really putting traces, virtual traces, on the physical picture of what the circuit board will look like, but there's no software connection between those two. That's a really rudimentary, simplistic kind of a tool, and I don't recommend those.
So that's kind of like a what you draw is what you're going to get, and there's no intelligence behind it. It's literally, if you screwed the board drawing up, I mean, all you've done is to find a drawing, you've screwed it up. Exactly.
So that's just it's like a mechanical drawing of where you want the traces. So that's really not the way a modern PCB tool should work. The way it should work is, the first step is you pull the components out of a library and compose your electrical schematic. And by doing that, you're defining the connections between the parts, so that when you go to your layout tool, that's already in the database. So when you start your circuit board, what you'll see is the boundary of the board, the edge of the board, as like a rectangle, let's say, and then off to the side in your layout editor will be the physical footprint, or the actual physical shape of the components will be already instantiated or sitting in your layout, but they'll all be kind of grouped off to the side because the software doesn't know where you want them yet. So if you actually are looking at the schematic and the layout at the same time, which of course you could do with these tools, if you pull a part out of a library and drop it on your schematic, that part instantly shows up on the layout. Now, it doesn't know where you want it. You have to drag it around and drop it where you want to put it, but it knows that part now exists. So this is a little bit of a pain in some ways, but it's super useful. The reason it's a little bit of a pain is if you want to do any changes to your layout, like I want to add another component or I want to put another trace on the board, most of the time you have to go back and put that thing in the schematic first. Otherwise, it won't let you just stick it in the layout. Now, there's a couple ways you can override that, but generally you don't, because you want to make sure that your schematic is completely in sync with what goes in the layout.
Well, I mean, that makes sense. I mean, it's like you're auditing your design in a sense.
Right. It's like I said, it's called correct by construction, so that when you go do the physical layout, all of the electrical connections have been predefined by the schematic. And in fact, in a good tool, if you override that in the layout tool, it will indicate that as a potential error, a mistake that you might have made. And maybe you wanted to do that or maybe not, but it'll flag that sort of thing.
And you mentioned this earlier, but I'm assuming this will work with either through-hole or surface mount stuff.
Yes, that's right. So when you look at those libraries, like in the Big Eagle library, and you go to pull out a resistor, you can pull out a 1/4 watt through-hole resistor or a 1/4 watt surface mount resistor. The symbol, by the way, may well be the same, but there's an attribute, a piece of data attached to that schematic symbol that tells it what the physical footprint is that symbol should map into.
So if it were a surface mount, it would tell you that the component is actually this big. This is how far away the solder pad should be and how big the solder pad should be?
Indirectly, the way they typically work is that when you create a component, this goes kind of back to the very, very beginning, which is creating a library of parts to begin with. When you create your library of parts, so let's sort of take a step back. Let's pretend you had no parts in your library, or maybe in the case of your power circuit, perhaps there's an integrated circuit that is not in a library because it's a new part. So what you'd have to do before you can actually make a schematic or a layout is you'd have to go into a third program, which is usually part of the same software suite, and create a component. And the component has two parts, a schematic symbol and a layout footprint. And both of those together are a component. So let's say we're starting from scratch and we want to build put a brand new part in the library. So what you do is you go into the component editor, and you have a blank screen, and you just draw squares and lines and circles and whatever shape you want to make that schematic symbol. So in the case of like a resistor, you have a horizontal line, then a squiggly up and down line, and then another horizontal line to make that little resistor shape. So that's the cosmetic shape of the symbol, and that's purely graphical. But before you're done, what you have to do is you have to add the connection points to that schematic symbol. So in a resistor, there's two sides of the resistor, and in the editor, there's a thing called usually like a pin, and you say, okay, I'm going to place a pin. And when you hit place a pin, then you put you click the end of the little line on the resistor, and you get a little dot. And that little dot means it's an electrical connection point. And you put two of those on your resistor, one on each lead. So now I have two connection points on my schematic symbol. So at this point, what the database knows is I have a symbol. It's called whatever you want to call it, Jeremy's resistor. It looks like this squiggly shape, and there's two connection points, and each of those connection points has a name. It's like input 1 and input 2 or something like that. So that defines your symbol. When you define the physical layout part, the footprint for that part, here's where you figure out, well, what do I want to show up on the circuit board? So let's say it's a 1/4 watt through-hole resistor. Well, what I'm going to want is two pads, and a pad is the round copper thing that you stick the lead of the component through, and you solder to it. So just like on the schematic, we had two electrical connection points defined. In the layout, we have two solder pads. So the layout you'll decide, okay, for each of these solder pads, how big is the diameter of the pad? How big is the hole for the lead to fit through it? And then what's the geometry of that? So I want to space that so that those two holes on the board are maybe 0.4 inches apart from one another. So that stuff you define in the layout part of the component editor. And you'll also put things like the silk screen. Silk screen is the white printed text or graphic you'll see on the circuit board, and typically it'll be the outline of the component. So you'll see like a rectangular box which represents the resistor with two pads, one on each end, and that combination of holes and geometry and that the printed silk screen, that creates the physical side of your component. So those two things together, the schematic symbol and the footprint, are stored in the library as your component. So that when you pull that resistor out of your library and stick it in your schematic, it automatically pulls out the physical footprint and drops it into the layout. And there's a one-to-one correspondence between the connection points in the schematic symbol and the connection points, the electrical connections in the layout part of that symbol.
Well, that's cool because I guess it makes total sense, but I never realized you could actually, design your own components for your own like personal library. In fact, while you were talking, I went to go look up that chip, which is the LT3562, to see if somebody has made an Eagle component for it, and I didn't find one. But it's good to know that you could put in the physical characteristics and whatnot and actually put it in your own personal library.
Yeah, and I do it all the time. It takes like 5 minutes to make a part. It's really pretty simple, especially if the physical footprint is the same. So, for instance, if you think about like an integrated circuit, let's say you've got a 14-pin through-hole integrated circuit package, the traditional chip that you've seen a million times. Well, if you look at all of the digital logic chips that exist, there's probably 100 of them of different kinds that have the exact same physical package. They're 14 pins, 7 on each side. They're 1/10 of an inch spacing between the pins, etc. So in that case, you only actually have to create that footprint once. So when you're in your component editor, I can say, well, here's the symbol of my component, which may be unique, and then I'm going to connect that schematic symbol to a generic 14-pin dual inline package DIP physical component package. So if I have 100 parts that all have 14-pin dip packages, I only need one library entry that's the 14-pin dip, and they all just point to that. So every time I put in that component on my schematic, it puts in the 14-pin dip package on my layout.
Now, talking about dips, so if anybody has ever seen an Arduino Uno board, the Atmel processor on there is a dual inline package component. I can't remember how many pins it has. But is there any logic that would keep you from doing dumb things? So, for instance, if I did have one of those Atmel like 328 chips, where I obviously have a couple of digital-only inputs, for instance, if I were to try to hook, say, a 12-volt rail up to it, would it keep me from doing that? Or is it you're completely on your own? Like, if you make there's nothing keeping you from making mistakes.
No, that's right. So, in most layout tools, if you hook up a bad electrical connection, it's your own fault. You suffer the consequences. So if you just said, well, I'm going to take my 5-volt supply rail and I'm just going to hook it up to the ground pin on the part, most of them will just let you do that because, well, you know better, and so there you go. There are some board layout tools that will do more electrical rule checking. So they will look at things like, is this an input pin or an output pin? Is this a voltage rail or a ground pin or a signal pin? And it might say, for instance, when you have a set of connections that are all power connections, don't allow that to be connected to a signal pin or a ground pin or whatever. So there are some things like that, but that tends to be in more sophisticated board layout tools. The big headache, though, is that for every one of those rules, you have to have somebody put that into the component definition. So a lot of times that's just not done. So the short answer to your question is generally no.
That's fair. I'm all about personal accountability. So that covers schematic capture, I think you said it was called?
Yeah, schematic capture.
So that covers schematic capture. Go ahead.
And just a couple other notes. So when you're doing your schematic, when you connect, let's say you do a 3-way connection, like I got a horizontal wire, then I have another wire coming down vertically, and I stop at that other wire. The software is smart enough to know, I want to make an electrical connection, and you'll know that it's making one because it puts a little solder dot on the schematic, a little dot where that 3-way connection now happens. So it understands that connectivity, and it's really quite smart. Like if you grabbed, let's say, a group of components on the schematic and you move them around, the wires on the schematic will, what they call rubber band. They'll stretch and move around while you're dragging that cluster of parts around the screen. So it's pretty cool, actually, once you get into it. It does things that you would kind of think it should do if you really thought about it. So they're pretty cool tools.
All right, so after I have my schematic captured, then what do I do?
So once you have the schematic, then you go to the layout side. And in the layout tool, like I said, you'll have your board geometry, the outline of the board, and you can make the board whatever size you want, let's say 3 by 5 inches. And then off to the side of the screen will be a pile of all those footprints of components that you've already hooked up in the schematic. And now you do what's called placement. And placement is simply dragging each of those physical part outlines to a place on the circuit board where you want them. So you move all the parts onto the circuit board, and of course, when you go to lay out the parts, you want it to look nice, so you want things lined up, and you want the traces typically as short as possible. So you put the parts that are hooked up together closer to one another. And when you look at the layout, the first thing you'll notice is that all of the electrical connections that have to be made are already indicated by a line that connects the pads together on the layout. So let's go back to our 2 resistor example. I've got 2 resistors, and on the schematic I hook a pin on each resistor together. So there's a wire between the resistors. On the layout, I'll see my 2 physical resistor packages, and there'll be a tiny little line that connects the 2 solder pads together. It's called an airline distance between those, because it's just a straight line. And you know what electrical connections exist by looking at the layout. That's not the actual copper. That's just a straight line between the pads. And as you move that resistor, let's say one of the resistors around the board, dragging it with your mouse, that little line will just track with the resistor, and you'll see it move around. And then you drop the resistor where you want it, and you drag the other resistor over next to it, drop it where you want it, and now you have those parts placed on the circuit board. But we haven't done any routing of traces yet.
Okay, so I mean that's literally just parts placement.
That's just parts placement.
Now, okay, so what I'm understanding about this line is it's kind of like a reminder that, hey, these two things should be electrically connected, right? It's not the actual trace. It's a guideline.
That's right.
One of the things, so one of the issues I've always had with technology like this is that, you know, when you're literally staring at a blank circuit design in this particular case, the infiniteness of possibilities is terrifying to me.
I know what you're saying. Yeah.
I mean, this is part of the reason why, like, I was a horrible programmer, is because there are literally a million ways to skin a cat. And I was always afraid of picking the wrong one, because invariably I would. Mm-hmm. And so that's one of the things, like when I look at the antenna analyzer board, and I realize that there must have been rhyme and reason to why every component on that board wound up where they wound up. Granted, our podcast run long, but I don't think we can fully cover all of the philosophy of parts placement, but are there some high-level guidelines?
Sure. Oh, of course. It depends on what you're designing. So some kinds of circuits
course, that's our default answer. It depends.
Yes, well, that's true. I mean, that's the way it is. So if you're doing a circuit that's very forgiving, you know, let's say you're doing a 5-volt power supply circuit. The length of the traces is not super critical. If it's not high current, the width of the traces is not super critical. So it's very forgiving. At the other end of the spectrum, if you're doing a high frequency digital board or an RF board, then the ground placement, the length of the traces, the width of the traces, all that stuff starts to really matter. So most likely for most hobby projects, it's generally not super critical, but there's guidelines you'd want to follow. So for example, shorter traces are better than longer traces. Fatter traces are better than skinnier traces. And there's a little bit more esoteric stuff, like, for instance, if you have a junction, like let's say there's a trace that connects into another trace, ideally you want that trace to be at a 90-degree angle, not at an acute angle. In other words, not at like 30 degrees, if you follow what I'm saying, because that little V of the 30-degree acute angle creates a pocket where you could, in the manufacturing process, it's easier to have defects occur in a small junction like that. Now, that's really only something to worry about if you're making a zillion boards. If you're making one hobby board, I wouldn't sweat it. But yeah, generally you want to make the board as small as you can and pack the parts in and make the traces as short as possible. General rule. Now, but it depends on the project.
Okay, so let me ask you this, because barring a project that's all passives, mm-hmm. Maybe you built a little analog amplifier or something. Mm-hmm. But if I got a project where I'm using somebody else's IC, somebody else's integrated circuit, and I have to lay it out with these things, like, do you normally start by putting the meatier components on first, like the main chips, and then put the passives around it? Do you start with the passives? Is any guidelines there?
Yeah, it depends on the circuit. I would say I tend to put the media, as you said, the meatier components down first. I look at the board and I think, okay, given this size, usually there's a size constraint. Like, I want to put the board in this specific box, and so the box defines the size of the circuit board, and then I have to figure out, well, where do the connectors go? Because those are going to be important. So maybe those get placed next, and then you have the space in the middle where all the parts go. And so you kind of think, well, okay, the signals go from this connector to this part, to this part, to this part, and you want to put those parts close together so you're not running traces all over the board. One reason to not run long traces, of course, is you want to reduce interference, but the more long traces you have, the more circuit board area you chew up, so the bigger the board has to be. So it all kind of goes back to shorter traces are better for a whole bunch of reasons.
So one of the things that, just to recap, I've built my schematic, which basically creates the electrical auditing to make sure the components on the board are connected the way that I said they should be. I'm assuming as I'm laying this thing out, I just have a palette with all the components. I'm pulling them down. Guidelines are being created. My goal is to keep things as close together as possible, keep traces short, keep them as big as possible, etc. So once I've kind of got component placement, when do you actually start drawing the traces?
Yeah, so that's a great question. So it depends on the nature of the board you're doing. Sometimes the traces are super critical. Like I've done some high current DC power boards where the traces are carrying a fair bit of current. And so it was very important in that design to have fat traces, as short as possible, and those were dominant. They took up big chunks of the circuit board, and everything else had to kind of be worked around it. There's other designs where that's not the case, and you could be a little bit more loose and free with where things go, because maybe the signals aren't very fast or they're not very sensitive. So you can kind of be more, a little bit looser. And it also depends on how tightly you want to pack stuff in. The tighter you pack stuff in, then the harder it is to assemble it. So, it depends on how much you want to cram stuff in there as well.
So, I guess, that didn't quite answer my question, because in my mind, let's pretend I have 10 components on this mythical board I'm working on.
Okay.
I bring a couple of them down. The guidelines are there. Do I bring a couple down, draw some traces, then bring some more down? Or do you lay out all the components and then draw the traces? Or do you draw traces one component at a time?
It really does depend on the board. So
I'm going to make a supercut of you just saying it depends.
So you're going to sample that? Let me give you an example. So I'm working on this baby repeater controller project. And in this, the audio section of that control system has stages. So there's 2 receiver inputs. Each receiver input has a buffer op amp with about half a dozen discretes, multiple resistors and capacitors for some filtering. So I look, and then there's a digital pot, and then there's another audio buffer, and then there's some switching chips, and there's another audio buffer, etc. So what I tend to do is since logically there's clusters of components in little stages of the circuit, I tend to lay those blocks out together in as little clumps of components, and then try to figure out how to best fit them in together on the circuit board. And in a way, your approach to this depends on how tight you want to pack the board. If you have a lot of real estate on the board, then you could be a little bit sloppier with how you lay all this stuff out. But generally, I tend to go by stages of the circuit. So like this audio circuit, the first thing you run into is there's an op amp with half a dozen resistors and capacitors. So I'll drop the op amp on the board. I'll put the associated resistors and capacitors clustered around that op amp, and then and that little cluster of parts will be in an area of the board, but maybe not exactly the final location. I can always draw a boundary around those half a dozen parts and drag them around as a unit. So not only the parts, but the traces in between the pins.
Oh, so it's like a grouping or a submodule.
Exactly.
That's cool.
It's a grouping. And now some PCB tools will let you maintain that as a group and drag it around in the future, and others you have to redraw the grouping every time. So the features are different. But yeah, so I would tend to say, well, like on that repeater controller, there's probably 7 or 8 clusters of components, and I'll lay out those little clusters, and then I'll bring the clusters in and place them on the board at sort of a macro level. Now, in that case, I'm not trying to overpack stuff. If I was really trying to shave off every, tenth of an inch of the circuit board, I might take a little bit different approach to how I do that layout. But that's usually a pretty good way to go.
Well, and I think for a lot of the stuff you design, sometimes you may have more of a target. Like you said, if you're buying an off-the-shelf like Hammond box, right, you may know what your target size is going to be. Versus if you're doing custom PCBs, you don't know what you're going to be working with. You may try to aim to keep the whole design as dense, as small as possible.
Mm-hmm.
So one of the things, it's like when I look at the specs for Eagle, right, there's like 15 different versions of Eagle. Mm-hmm. Based on whether you're going to use it commercially, whether you're a maker. And one of the things that it talks about are PCB layers.
Right.
Enlighten me.
Yeah. So let's talk about what a PCB actually is physically. So a printed circuit board at the core is a piece of fiberglass. And you'll hear that there's different kinds of materials that they make printed circuit boards out of. The most common material that's used is a form of fiberglass called FR4, Foxtrot Romeo 4. So if you're making a hobby circuit, odds are it's on FR4. That's kind of the mass quantity, low cost, perfectly fine circuit board material. I've pretty much only ever done circuits on FR4 material. There's more exotic stuff that's primarily used for much more higher frequency designs, which hams are probably never going to get into unless you're making some microwave circuit. So anyway, the core of the circuit board is a piece of fiberglass, and the typical thickness of it comes in a variety of thicknesses, but the most common thickness is about 0.0625 inches in thickness. The layers refer to the number of copper trace layers that are on that circuit board. So the most basic circuit board you could make is a single layer board. What that means is that I have my fiberglass, which is an insulator, and then on the bottom I have a layer of copper, and all of my traces will be made out of that copper that's laminated to the bottom of the circuit board. So that's a single layer board. The most common boards in the hobby world are two-layer boards, where you have a layer of copper on the bottom, the fiberglass in the middle, and then another layer of copper on the top. So that's a two-layer board. And with a two-layer board, you have components which are mounted on the top, sometimes also on the bottom, and you have traces on the top and the bottom. And then you can connect between the top and the bottom by drilling a hole and plating that hole, and that forms an electrical connection between the top layer and the bottom layer. By the way, that's got a name. That's called a via, V-I-A. So if someone says, well, we're going to put a via right here, what they're saying is we're going to take the electrical connection, let's say on the top layer, and I'm going to move it to the bottom layer. And the way I do that is by having the machine drill a hole and plating that hole, so the electrical connection now goes to the bottom layer.
Well, that's cool.
So two-layer boards are super common. They're very inexpensive to make. And for ham radio projects, and 99% of the stuff we would ever do, a two-layer board is fine. Now, in the commercial world, you can have many, many more layers. It's very common to make a 4-layer or 6-layer board. Often you'll use 4 layers when you either want a layer in the middle to be a shield, like a ground plane, to isolate the top and bottom, or a 4-layer board is often used where you want to put power and ground signals on the let's say the 2 inside layers, and you want to put the signals on the outer top and bottom layer. So a 4-layer board is popular, but of course it's more expensive to do a 4-layer board. So the advantage of a 4-layer or a multi-layer board is you have more routing resources, more real estate to route traces between parts, which means that they could be dense, a greater density of components. But the downside is it's going to be more expensive. And if you're doing a hobby board, let's say your linear technology power supply circuit board, and you said, well, I could do it in 2 layers or 4, you're going to pay a premium of maybe 40% more expensive to make a 4-layer circuit board than a 2-layer circuit board.
But to that point, there may be, well, actually, that's one of the interesting things, right? Because at the end of the day, I'm assuming you can still only put components on the outside layers.
Well, in the normal world, yes. I mean, there actually are techniques to make to have what are called buried components inside a circuit board, but that's a really exotic thing.
That sounds well beyond the scope.
That's something that none of us will ever do that. So right.
At the end of the day, though, if you do have those multiple layers, all those are copper traces, right? That, like you said, they're just signal lanes.
Right.
So it doesn't necessarily give you more density. So it's not even the type of thing where you could say, oh, well, I can do a big 2-layer board or a small 4-layer board.
No, that's exactly the point. So if I have a ton of signals on the top and bottom layers of my board, often if you went to 4 layers or 6 layers, I mean, I'll go in pairs, or 8 layers, then you could probably shrink the size of the board. Because when you look at the board, the biggest problem, a big problem in making a board is the routing congestion. And some circuits have few wires, and some circuits have tons of wires. And if you have a circuit with lots and lots of connections, then a multi-layer board will allow you to put multiple traces over one another and not have them short out, and that thereby making the board denser. So so if you look at like a lot of higher end commercial pieces of equipment or even consumer electronics, they might have 6, 8, 10 or more layers. I worked for a company one time, and we made a large piece of electronic equipment, and our circuit boards were 32 layers.
Wow.
And at that time, and this goes back 15, 20 years ago, at that time, that was kind of pushing the state of the art. And these were very large boards. They were about 20 inches or more on the side. So they were physically big and had over 30 layers. And there were only a couple places in the world that could fabricate the boards at the time. So it was a very expensive board, to say the least. And the reason for that, in that case, is that we had a big array of FPGAs, these big field programmable gate arrays, and there were so many pins on every part, and there was so much interconnection in the architecture of this device that we had to have a zillion layers. But I mean, back to reality, for ham projects, 2 layers is fine for probably maybe every project you ever do. I personally have rarely ever done a 4-layer board, and I'll give you a good reason to avoid a 4-layer board. In a 4-layer board, if you make a mistake, there's no way you can cut and jump the mistake if the mistake is on an internal layer.
Oh.
So imagine it's often the case that you make a mistake, as I have found. So let's say you inadvertently cross 2 traces, and the tool dutifully makes a connection there, and you never meant for the connection to exist. If that is on the outside top or bottom layer, you could sit there with your X-Acto knife and cut the trace and wire a jumper, and you can make it work. If that short is on the inside layer, well, you're toss the board out. There's no way to fix it.
I gotcha. Now, another thing that I'm assuming, like when I look at the DV Mega, it has an SMA connector on it, but this SMA connector is more than just solder to the board. It actually has 4 corners that actually go through the board and give a really good mechanical connection. So I'm assuming you have options to do things like that as well.
Mm-hmm. Yeah, well, when you pick that part, let's say you pick that SMA connector out of the library, the footprint for that part would be the center pin of the SMA plus the 4 pins for the ground. So that's all part of the footprint.
Okay. Now, going back to the routing question, I notice if I look at the spec sheet for Eagle, which, by the way, one thing that's really topical about us talking about this is there was a big update to Eagle to version 7.7, I think just in the last couple days. But I noticed one of the features they tout is something called auto routing. Now, on the other hand, if you listen to the EEV blog, people make fun of auto routing. What's auto routing?
So let's go back to before we answer that, let's go back to the manual version of that. So you've got your schematic done, and you bring up the layout editor, and here's your big pile of parts off to the side with the little air lines between the pads, but those are not copper traces yet. So you place your parts, and once the parts are placed, then you manually convert those little airline connections into actual traces. And so you'll pick an airline wire, and you'll say, make this a trace, and then you'll see a line appear that has a width, and you could define the width, and then you basically draw that trace where you want it to go on the board to connect the pins together. So that's manual routing. So routing refers to figuring out the path that the copper trace will take across the board between the connection points. And for a small, simple board, manual layout is perfectly fine. Manual routing is totally okay. Now, on a big board where you have a lot of parts with a huge number of pins and therefore a huge number of traces to be connected, that's very tedious to do by hand. And so software has been developed over the years to do that for you automatically. So an auto router is a piece of software that takes the known interconnection that you've already defined in the schematic, and it figures out where it's going to draw the traces on the circuit board, and it'll do it in a fashion that gives you an optimum layout, or at least it's supposed to. So that what that means is, let's say I've got a part on two parts on either side of my board, left and right side, and the traces have to connect between those parts. Well, a straight line would make the most sense. What if there's something in the middle? If there's something in the middle, then you have to route that trace so it goes around the object in the middle and then to the opposite side to the other part. Well, the auto router is smart, and the auto router looks at this and says, okay, I have a set of rules I'm going to operate by, and I'm going to lay that trace down so it's as short as possible, and it will not clash with any other trace and create a short. So the auto router's job is to make all these physical connections for you and do it in a way that does not violate any design rules.
Okay. But I'm assuming that once you run that, like you said, you can tweak it.
Oh, yeah, you can tweak it. So the theory is that the most advanced version of this is you not only have auto routing, you have auto placement. So auto placement and auto routing work together to decide where to put the parts and how to hook the parts together to achieve a set of goals which you've defined in a set of rules, like make the traces as short as possible, et cetera, et cetera. Now, that's the theory. The practical reality is that it's very difficult to write a really good auto router, and the very expensive commercial tools that, let's say if we were a big company and we made fancy electronics, we would use some really expensive software that does this auto routing and does a really super job of it. At the lower end of the product spectrum out there, the auto routing technology tends to not be so great. And also the complexity of the boards are not that bad. So you really don't need auto routing. So for me, like when I use Eagle, for instance, I've got the auto router and I've run the auto router to see how it does. And sometimes it gives me a layout that I like, and sometimes I don't. And I would have done it differently if I were doing it. And my boards are not that dense, so I just I always do the routing manually. I don't really bother with the auto router.
Well, okay, that makes sense. Now, we've talked about different PCB size, and one thing I do want to call out, because I noticed it looks like Eagle, for the most part, the feature set is pretty flat across the different versions. So, for instance, there's Standard, Premium, and Ultimate are all... basically, when I look at these three, the thing that changes is the number of schematic sheets and the number of layers, and then your total area. Mm-hmm. And as you pay more money, you can build larger boards. What does the schematic sheet mean?
So when you go into the schematic editor, imagine like we're talking about our diagram with the two resistors. Well, when you look at the screen, you could put a lot of parts on the screen, but at some point, if you have a really big design, you want to break it up. And so, imagine you're in PowerPoint, but you only had one slide. Well, if your whole presentation was one slide, you're fine. But if you're trying to make 5 points and you want a slide for every point, well, you're going to run out of space. You need multiple pages. Same thing is true in a schematic. So you might have to have multiple pages of your schematic. And sometimes it's because you have too many parts. You've got to spread it out. And sometimes it's just that you want to logically group it. So you might say, for instance, on one page, I'm going to put my power supply circuit. On another page, I'm going to put my connectors. On another page, I'm going to put my processor and the associated support components. On another page, I'm going to put my analog circuitry. It's just a way to organize things in a logical fashion.
Well, it's even kind of like you were talking earlier about grouping kind of like the discrete signal amplification parts in that example you gave earlier.
That's right. Now you might at this point say, well, okay, but if I have multiple pages, how do you connect between the pages? Because the way you connect on a page is you draw a line between the parts, pins, and there's now an electrical connection established in the database. How in the world does that work when you have 2 pages? And the answer is something we really didn't talk about when we talked about the schematic at first. And that is that electrical connection between those 2 resistors, pins we've been talking about, that wire or that trace, that electrical connection has a name. So when I draw the wire between those 2 resistors pins, it just looks like a line on the schematic. If I click on that wire and say, show me your attributes, one of the attributes of that wire is going to be a name. Now, in board layout lingo, that connection is called a net, N-E-T. So the word net refers to a connection between pins of 2 or more components. So that net has a name, that wire has a name, and every wire on the page has a unique name, and the software automatically assigns a name to every wire, and you just don't have to see it on the schematic. Now, there are some wires that you might want to give a name to yourself. So, for instance, you might want to call the ground signal ground or GND or whatever, GD, whatever characters you like. If you have 2 wires on a schematic and they don't touch each other on the diagram, but you name those 2 wires the same name, they are electrically connected in the database. Now, let me give you an example of that. How many times have you seen a schematic where the ground of a circuit is a little ground symbol? And you'll see like a capacitor to ground symbol, another capacitor to the ground symbol. And when you look at that, you know that those are electrically connected because they're both touching the ground symbol, but you don't see a wire between them on the schematic because the convention in schematics to simplify and like take the noise out of a schematic diagram is, well, for certain signals like power rails and ground, you can just use a symbol and not draw it actually as a wire because it gets really messy that way. Well, in the schematic editor, when you name this wire GND and you name that wire GND to the software, they're connected. And if you were then to look at the layout, those 2 points that had the same name in the schematic, you'll have the airline between those 2 points in your layout. So when you have 2 schematic pages, in most of these editors, there's a technique where the name of a net on one page, if it's got the same name as another page and they're global names, they will be connected together like ground.
Well, that's pretty handy.
Yeah, it's very handy. So that way, you can, for a system-wide net like 5 volts, my 5-volt rail, I want the system and the layout to think of that as all these parts are hooked up to 5 volts, even though 5 volts is spread across the schematic, and that's accomplished by either having that net name be the same, or in some cases you can put a symbol on there. So here now we kind of get into the peculiarities of the different layout tools or schematic editors. Some of them, for instance, if the net name on one page is the same as the name on another page, they're not connected unless there's a little symbol that terminates that net on the schematic. And if the symbol has the same name, then they're connected. It's called an interpage connector. Other systems, as long as the net has the same name, they're electrically connected. So these are some of the nuances you kind of have to get into and figure out, how your tool works. But that's the idea behind multiple pages and some of the subtleties about how you make it all connect together.
Okay.
By the way, if you don't understand how that stuff works, you can imagine how you can really mess yourself up. Like, well, I'm going to use 2 pages, and you do your 2-page schematic, and then you go to the layout, and nothing on page 1 is connected to anything on page 2 because all the names are different.
Yeah, so in other words, if you have a development background, they all share a common namespace in a given project.
Yeah.
Cool.
Yeah, it's like a pointer to the same thing.
So that kind of explains the layout. So we've gone from you have a library of parts, or you can define your own parts in a library, and that covers some characteristics as far as what they do as physically, as well as what would need to be actually on the board as far as silk screening and pad size and stuff. You draw your schematic, and then you take the schematic from the schematic capture into the layout portion of the software. You drag your components down. There are guidelines. You draw traces. When you are done and you have your perfect circuit board, I'm looking over at my printer. I don't think it prints circuit boards. Mm-hmm. So right. What do you do after you get that layout done?
Yeah, so once you get the layout done, then you generate a set of data files, which then go to the fabrication house to manufacture the boards.
So I've heard the name Gerbers.
Mm-hmm. Yeah, Gerbers.
Isn't that what I feed my son?
Yeah, I think it's a different Gerber. So that's one of these names that came about, in the old days that we still use them today. So in the old days, there's a company called Gerber that made a photo plotter, and the photo plotter basically would take the data file out of your layout tool, and it would use that data file to photo plot the mask information on the film that was used to manufacture the PC board. So in other words, the trace that you drew on the physical board layout tool that said, okay, start the trace at this XY location and make that trace 0.05 inches wide and have it go to this XY location. All that numerical information is stored in your layout tool. That's the information that you have to give to the photo plotter to make the film, to do the processing and the manufacturing of the board.
Oh.
So the vendor of those photo plotters was Gerber, and so they defined the format of what that data file looks like. And so when you generate your Gerber files, you're generating the photo plot mechanical information. So at that point, you completely lose any notion of electrical information or symbols or anything like that. What you're really pulling out of the layout tool is only the physical manufacturing data that you need to have the manufacturing process build your photo plots. So what's in that Gerber data is all this XY location stuff, like the trace, or go to this XY location and drill a hole of a certain diameter, etc. So those are Gerbers. And so when you go to manufacture your board, so like I said, up to now, we've had the schematic and we've had the layout. In most tools, like in Eagle, there's a file which is your schematic and there's a file which is your layout, and they have the same name, but one is a .sch file, one's a .brd file for schematic and board. Those are the design tool files that you're editing. When you go to manufacture that stuff, there's a program that you run inside the layout tool that extracts the necessary data into a set of data files, your Gerber files. And for a typical, let's say, 2-layer circuit board, you're going to generate about 7 files. And you take all 7 of those files and you ship them off to your board house and say, make me 10 boards. And that's all they need is that those Gerber files, and they'll use that to make the boards. So what's in those files is there's one file for each layer of your copper traces. So in a 2-layer board, there's a top and bottom trace file. There is a silkscreen file for top and bottom. In other words, the usually white lines and text that are printed on the tops and bottoms. There is a photomask a pair of files for the top and bottom. The photomask is ever see like the green stuff on the circuit board?
Oh yeah.
Okay, and then around the pad, that green stuff's not there, right?
Yeah.
So that's the photomask, and what the photomask does is it's like an extra layer of stuff, so that when you flow solder the circuit board, the solder will naturally be attracted to the copper pads, and the photomask will keep the solder from going anywhere else. It'll prevent bridging between pads. And then the last file, the 7th file, is the drill file, and the drill file basically says, here's all the XY locations and all the drill hole sizes that have to be poked into the board.
So how do earlier we were talking about drilling between the layers and then filling it with, coating the inside of it to have a trace. Mm-hmm. How's that done?
It's all automatically done for you. So when you do your board layout and you say, okay, I want to go from the top layer and I want to transition to the bottom layer, all you do is you click on that trace and you say go to the bottom, and then the layout tool automatically sticks in the via, which is that the hole, and also enough copper pad on the top and bottom to connect it properly. And then when you generate these Gerber files, all that is just generated for you. So you don't have to think about any of that stuff. That's all handled for you. In fact, you never even look at the Gerber files. Normally, you just generate them and then you
package
zip them up
and ship them on.
Ship them off, and there you go. Now, from the circuit board manufacturer's perspective, when you say, here's my Gerber files and here's my credit card, they have license to make your circuit board. Whether you got it right or not, that's your problem. Their job is to faithfully manufacture the things that's in that Gerber file. So they're off the hook as your stupid electrical engineering problems go. So if there's more than once that I've done a circuit board where I've had 2 traces overlap each other, like a cross over each other, and have a dead short that I didn't intend, because I thought that one trace was on the top and one was on the bottom, and they would fly over each other. And in fact, by mistake, they were both on the same layer.
Oh, yeah. That's a problem.
That's a problem. And so from the manufacturer's point of view, hey, that's what was in the file. That's what we made, because they have no idea what it's supposed to look like.
Yep.
In fact, you don't even send them the schematic. You don't even send them the board layout file. You just send them the Gerbers.
Well, cool. So if you've gone to this process, you've designed it, and you want to actually get it made, do you have any recommendations for where to send the Gerbers off to actually get made?
In the old days, it was kind of old industry. You'd have to go to some big company, and they wouldn't want to mess with you as a hobbyist, and it would cost an arm and a leg. And that's really changed with a lot of things that are more automated and turnkey in many industries now. Circuit board design has gone that way. So there's a lot of places where you can go make as few as 5 circuit boards or even 3 circuit boards at kind of a reasonable price. So there's a ton of them out there, and you could just Google low cost, low volume PCB prototyping, and you'll get 50, 100 hits. There's a few that I've used a bunch myself that I would recommend. So I tend to use one of 2 kinds of board houses, either ones where I'm willing to put up with a long lead time to get the price down, versus ones where I need a board like in the next 3 days and I'm willing to pay a premium for that. So like here in the Bay Area, there's a zillion board houses, and I've used one called Sierra Circuits, and they're a normal, traditional, high-end production facility, but they have a, quote, low-cost service where they call it the no-touch service. So with no touch, you give them the Gerbers, they make what you give them, they give you the boards, they're done, and they'll do it in 2 days, 3 days, 4 days, a week, 2 weeks, and the faster you want it, the more you pay for it. But the nice thing about these guys is I could drive to their office and pick up the boards the day they're ready. So I could get something done in, let's say, like 4 days, and have my 2 or 3 prototype boards ready to go. I don't do that very often because it's kind of expensive. So most of the boards that I make are through these low-cost services. And there usually is a 1 to 3 week or sometimes more lead time, because what they're doing is they're aggregating multiple orders together. So if they were just going to make my circuit board by itself, that would be kind of expensive. So what they'll do is they'll wait till they get enough orders, and they'll take all of these boards from different customers, and they'll put them all together in one gigantic board, fabricate the one gigantic board, and then chop them up. And then we all get our little pieces, and that brings the price down. Now, as a customer, you never see this. It's just you send them the Gerbers for your little board, and you get back 5 of your little board. You're done. But those services tend to take like 2 or 3 weeks turnaround. And if you're willing to wait 3 weeks, then that could be very reasonable. So I'll give you an example. When we if you're doing a prototype and you have to make, let's say, at least 3 to 5 boards, 2-sided boards that are solder masked, silk screened, so completely professional, excellent quality boards, you're probably looking at $50 to $100 for 5 boards. Now you can say, well, okay, well, I only needed 1, so is it really worth $100? Well, almost every project I build, someone else wants to build it eventually too. So I may want 2 or 3 myself. So it's not that bad. So, $10 or $20 for a board is not that bad. If you compare that to the old days where you'd get a vector board for let's say $10 or $15 and then have to hand assemble it all, what a pain. And it looks like, some junky prototype. Now, if you're going to go into volume, by the way, instead of making 5, you want to make 100 of something, then the prices come down significantly. So let's say you're doing a board that's 3 by 5, and it's 2 layers, silkscreen photo mask. You're going to make 100 of them. With shipping, which starts to become an issue when you're going overseas. So the price of the fabrication of the board and shipping, you could probably get that down to under $5 a board in some reasonable volume. So, if you're doing a club project or you've got some little product idea, you want to make some gadget, and you can imagine yourself making 50 or 100 of some of these boards, the prices are pretty reasonable.
Yeah, that doesn't sound too awful bad.
Now, there's others that are cheaper too, so you can shop around and you can find some deals that are as cheap as maybe $5 or $10 a board, even in low quantity. But then you start to get some restrictions, like there's maybe no silkscreen, or they're small. They can't be over a certain size, or not over a certain number of components or connections or whatever. So, you can get some things even cheaper, but maybe not the big project you're working on would be right.
Okay. So are there any other, I guess, the bigger, more modern companies that you've worked with before for this?
Who would I suggest?
Yeah.
Oh gosh.
I've heard names before. Like I've heard the name Osh Park.
Yeah, well, Osh Park is so okay. Let me give you a couple of. Here's some low end, not quality, but lower
affordable.
Yeah. So Osh Park is an example. Osh Park, you could do low quantity boards. The outfit that I've used mostly is Seed Studio, and Seed Studio is really famous for being a kind of medium low price supplier of hobby electronic stuff like boards and components and sensors and stuff like that. And they have a PCB service that is very, very good quality and very reasonably priced. It's in China, so you email your Gerbers to them, and 3 weeks later your boards show up. But they're all really good quality. I've been very happy with those guys.
See, I had no idea they did. I only know them because there have been several ham projects. Like there was, I think it's RF Anywhere was the company. Like they had a low end spectrum analyzer that you could buy from Seed. The original SARC antenna analyzer, which was a very nice unit, I think was also available for, like, I didn't realize that they did this manufacturing stuff.
Yeah, so they started out being just a component board, breakout board supplier, and they added PCB aggregation services, and now they've added assembly services also. So if you want to do a small surface mount board with the components in their library, and they have like a 100-part library of standard common parts, then they'll actually do assembly in low volume at low-ish prices. Frankly, the biggest headache in making your own boards is assembly. The actual manufacture of the raw circuit board itself, you could do that in a lot of places at some pretty aggressive prices. The problem is assembling it. So if you're going to assemble it yourself, no problem. But if you want to do, let's say, a board with a couple dozen surface mount parts, very tiny ones, and you don't want to hand solder them, you want them to do the assembly work, then it starts to get expensive.
But it's nice to know that you have the option.
Yeah, you have the option. In fact, the reason why most of the boards that I make are through-hole is because I want to hand assemble it, and I really don't want to hand assemble a surface mount board, especially the really tiny parts.
Yeah. Well, I mean, actually, to be fair, that was one of the things when I first started talking to you about this LT36 whatever chip. It's a fairly small surface mount package. Mm-hmm. And I actually think I found somebody online who had designed what has largely become known as a breakout board, where they manufacture them and they take all the tiny pins on the chip and put them into, traditional 0.1 inch pitch things that a human being could actually solder.
Yeah. Yeah, actually, that's a great tip because a lot of the parts are only available in surface mount, a lot of the newest parts. So if you can get these little breakout boards, the board you design, you could do all through hole, and common components like resistors, connectors, capacitors, some chips could just be soldered straight to the board through hole, and these wacky surface mount parts, the little breakout board, could be soldered in like a big component. And that's a totally reasonable way to do it. And that's an easy thing to assemble. You don't have to pay them to do the assembly. You just do that.
Well, that's, one of the things that I've really appreciated Adafruit for is they have a lot of really tiny components they put on breakout boards and make them usable.
Well, in fact, let's talk about the antenna analyzer for a sec. So one of the things on the antenna analyzer is an Arduino, and we're using the Arduino Pro Micro. And the CPU chip, of course, is a surface mount quad flat pack package, and we don't want to give that raw chip to the listeners to have to hand solder this tiny little surface mount part. So it's easier. In fact, it's easier and cheaper to have one of these Pro Micro Arduinos that's about 1.5 inches by maybe 3/4 of an inch or so. And that circuit board has the processor chip and some support components and a USB connector. And along the two long line edges of that board are 10th inch headers like you're describing. So once you put those header connectors on that little circuit board, it's like a big part. And so the antenna analyzer circuit board was designed with these 10th inch center through hole places, and you drop that Arduino board into it like a big part. So that way, no surface mount soldering, and you don't have to pay for any automated assembly. You could just do the whole thing by hand yourself.
Well, cool. Now, I think at this point we've kind of given a good high-level introduction to all of these components. Are there any last-minute tips or tricks or resources, any other recommendations you would give?
The nice thing about board design is that there's a ton of resources on the web. You can go to YouTube and just type in designing PC boards, and you'll get tons of videos. The EEV blog has some really good ones too, that not only does Dave Jones show you some tips about board design, but he's got some great videos about the manufacturing process, which frankly for us is just like a black box. We do the layout, we send the Gerbers off to some place, and somehow magically the boards show up. What happens in between is actually pretty interesting, and you can see all kinds of videos, either from Dave or from others on YouTube, that show you the manufacturing process, and it's really interesting to check it out. You should see it to appreciate. When you say, well, I paid $20 for the circuit board, that seems like a lot of money. Well, when you see what actually happens, it's a miracle. You can get it done for $20. So that's a lot of fun to check out. So I would look at YouTube videos. Most printed circuit board tool companies have tutorials or YouTube videos. I would check those out too. Eagle's no exception to that. So there's some good Eagle materials. One of the reasons I suggest a tool like Eagle is that the community is really big, which means that there's lots and lots of libraries already developed. There's lots of people who can answer your questions about how to use the tools. There's a lot of tutorials, videos, printed tutorials you can get on the web. So, just Google search. And you can also try a search for something like printed circuit board design tips. That's good because you'll learn a bunch of things like how far should you spread traces, how much current can you handle on a width of a trace, things like that are maybe not obvious when you're starting out and are really helpful in making things that are reliable.
Yeah, that's a good tip because, in some of the other things we've talked about where you might actually be handling a fair amount of high current 12-volt power, these little tiny signal traces aren't going to do it.
That's right. And there's multiple factors there. So like if you are pulling, let's say 20 amps on a circuit board, the current capacity of that trace is a function of the width of the trace and the thickness of the copper. And not all boards have the same thickness of copper. And when you look at, let's say, pricing out making circuit boards, one of the factors that they ask what you want is the thickness of the copper. And it's usually expressed, oddly enough, as ounces. Like, do you want 1 ounce copper or 2 ounce copper? Not that it's really significant, but 1 ounce copper is typical. That's the default in most cases. Well, if you go to 2 ounce copper, you can handle roughly twice the current for the same trace width. So that makes a big difference. So yeah, the trace width, of course, it's more expensive. It's about 50 to 60% more expensive to go to a thicker copper. So all these things kind of factor into your decisions of what to use. But the thing I would really suggest is this is not that hard. It's not. You're not going to sit down and by the end of the afternoon be banging out some complicated board. It's going to take you a little bit of time to get the hang of it. It's like learning any tool, and you might have to create some components in the library. And the first circuit board you make is probably going to have some fatal error. Mine certainly did and still do. But I've come up with some techniques for trying to avoid that. And it's like the more you do, the more you learn. So I think if you're an active builder and you want to have a really professional looking quality job done, I think making your own boards is a great thing to do.
Well, it's one more dimension of makerism, right?
Yeah, I mean, for sure.
I don't know, after having sat here and had this conversation with you, I actually feel like this might be approachable. Another thing, when you install Eagle Express, like there are actually even some sample boards that you can look at for different things. I noticed they even include the Arduino Mega 2560, which that's a behemoth.
Yeah, that's a great example because you'll see it like all kinds of different sizes of parts and through hole and surface mount and silkscreen, and it's a great example.
Well, George, thanks for sharing this information.
Oh, my pleasure. And I think back to one of the things you mentioned earlier, Jeremy, the forums on the Ham Radio 360 webpage. On the Workbench section there, if people have questions, you can post questions to the forum or on the Facebook site, and I'll be happy to answer questions.
All right. Let's take a break, and when we get back, we will answer listener questions.
The Workbench is sponsored by our friends at CADSoft. You know, they're the makers of the Eagle PCB design software, the very software George used to design the Pac-10 Classic, Pac-10 Mini, what him and Barrick are using to create this new antenna analyzer project for you here on the Workbench. You know, they got hundreds of parts libraries, tons of reference designs, and a monster huge user community. Eagle's a great choice for your next ham radio project, and you can get your free copy of their software today. Click on over to cadsoft.io and start getting your project put together today.
All right, so for questions this week, we'll start off with a question from David, AI6OU. David, AI6OU asks about antenna tuners. The internal ATU in my radio is inadequate to tune a random wire. Big question. Push button automatic or a manual tuner? I am leaning towards the manual tuner so I can actually learn a little more about tuning an antenna instead of pushing a button. But then again, the convenience of that button certainly speeds things up. Pros, cons, please discuss. So this is a good one. Let's start off quickly. An antenna tuner is a very poorly named device. Because it doesn't tune anything. Really, all it does is it should be called an antenna matching unit, should it not?
Yeah, that's a fair bet.
And effectively, what an antenna tuner is generally comprised of is some series of components that will match the impedance of the antenna to the radio to keep you from blowing your radio up when you transmit into a non-tuned antenna.
Yep, exactly.
So you're talking about what? Inductors?
Inductors and capacitors.
Yeah. And so on a manual tuner, you generally have, I'm assuming, a crank for inductance and a crank for capacitance, or a knob or a dial or something.
Yeah, well, and of course it depends on the kind of tuner, because there's different configurations of tuners. So you can have, typically the most common is one inductor and two capacitors, but you can have one capacitor, you can have a tapped inductor. I mean, there's all kinds of different configurations, but typically one inductor, two capacitors.
And then, of course, on the automatic front, you have a circuit board that have all these things on them, and then a ton of relays. And you press a button, it transmits a carrier, and it is constantly measuring probably SWR as it moves the relays to try to hunt down the combination of capacitance and inductance that will get you the best match.
Correct.
Probably the biggest name still making manual tuners is MFJ. The biggest name and most popular making automatic tuners is LDG. There used to be a company called SGC. I don't know if they're still in the market for automatic tuners, but I know those are very popular. And then automatic tuners. Okay. So automatic tuners are also available from ICOM, Yaesu, and I notice, generally speaking, you'll see two flavors. You'll see ones that are meant to go next to the radio and ones that are meant to be mounted at the base of the antenna. Mm-hmm. And of course, I've never seen a manual tuner meant to be mounted at the base of an antenna, because that would make it awful hard to use.
That's right. Now, by the way, some people do homebrew their own tuners, where instead of using switched L's and C's, they'll have like a little servo motor or something like that. But that's a little bit fringy.
Well, then those people can use Eagle and design their own PCBs.
Exactly.
This guy's asking about commercial off-the-shelf products.
Yeah. What would you suggest?
Well, horses for courses, I guess. The long and short of it is generally speaking, I think for a given manual tuner, you are going to be able to match a wider range of mismatched antennas, whereas some automatic tuners, especially the ones that come from the manufacturers like Kenwood, ICOM, Yaesu, the automatic tuners built into your radio generally won't match more than a 3-to-1 mismatch. If you get into an LDG, I think they go up to 20-to-1 or 10-to-1 for sure. I don't remember. I know that if you want speed, you go with the automatic tuner, because it will hunt it out in under 30 seconds. The nice thing is these tuners generally have memories, and so the next time you go to tune up on that frequency with that antenna, it will have already memorized the setting, and so it pretty much changes instantaneously. Whereas with the manual tuner, you're trading expediency for probably a better price.
Potentially better price, yeah. That's probably true. But, the auto tuners are really inexpensive these days. So I haven't really compared the same feature set between a manual and an automatic tuner. But, you're usually looking at a 100-watt tuner at a couple $100. And so maybe you can spend $100 for a manual and $200 for an auto tuner. But, it's somewhere in that range.
Yeah, and that's what I was going to say. I think like an LDG AT100 Pro 2, which is my favorite auto tuner for a 100-watt radio because, number one, has 2 antenna connections, and actually the meter on front will give you an indication of the match, or the SWR, as well as can serve as a power meter, rudimentary power meter. But I think it runs at like $220. It's slightly over $200, but it's a great tuner, and you can get cables to make it one push operation from ICOM or Yaesu radios. I've never tried to price a manual tuner because I've never had occasion to have one because they do tend to be rather large.
Well, the size is usually dependent on the power. So there's QRP tuners, there's 100-watt tuners, and then there's like big kilowatt tuners, and they do scale in size depending on the amount of power. The auto tuners for the given power they're about the same or slightly smaller. So size is really not a big factor for the most part. I think the big difference really is, do you want to twist the knobs or do you just want it done? And I think Dave's question implies that if you have a manual tuner, somehow you'll be more educated about how a tuner works. And that's kind of true the first time you actually use it. But every other time, it'll just be slower and inconvenient, in my opinion.
And it's not going to teach you anything that reading one paragraph won't.
Yeah.
I mean, to your point, you would know what the actual like inductor and capacitance settings are for a particular tuner or antenna. Of course, on the other hand, it also depends on your usage. I buy auto tuners because I'm mostly operating portably, and I don't know what the conditions or what antenna I'm going to be using. If you have like an off-center fed dipole that you're stringing up in your tree, and that's going to be your antenna, and it's not going to move, then knock yourself out with a manual tuner because you're going to remember what the settings are for the band positions, and you're going to write them down, and that's what you're going to do, and you could become quite fast.
But even with that, I would argue that if you know approximately where the capacitor setting is, you're still going to have to peek and tweak it by looking at the meter while you're keyed down and transmitting, because it'll be off a bit. Well, it depends on the antenna, but it'll probably be off a bit. So I think in all cases, the manual tuner is just going to be, it's more work. It's just kind of grunt, unfulfilling effort, in my opinion. And
on top of that, if you want to consider being good neighbors on the bands, we've all heard people with auto tuners tune up where you hear the tone, but it only lasts for, maybe 10 seconds. Whereas if you're using a manual tuner and it is taking a long time, you're going to be transmitting a carrier or a tone for longer, thereby polluting the bands.
The only reason I could see these days of getting a manual tuner is either one, the manual tuner that you're getting has a very wide tuning range, but even the best auto tuners are pretty much comparable. Number two is the manual tuner takes no power ever, where an auto tuner does require some amount of power, albeit minor. So if you're doing QRP and every milliamp of current counts, do you want an auto tuner or do you want a manual tuner? And I'm sure somebody could argue that a manual tuner would be better because it doesn't draw any power. So, okay, that's fair. But this day and age, the auto tuners are so good. I just don't see a reason to have a manual tuner. Not that they're bad. I mean, there's nothing at all wrong with them. It's just, the third reason to get it is probably price. They're going to be a bit less expensive.
I would agree. I mean, at the end of the day, I'm going to recommend an LDG AT100 Pro 2. The only other reason I could see to buy a manual tuner is if you have like a legal limit amplifier, buying a manual tuner that'll handle, 1.5 kilowatts is going to be a lot cheaper than buying an auto tuner for 1.5 kilowatts.
Yeah, fair enough.
So we're saying go auto.
Yeah, I think that's the better choice. I think for pure operating convenience, I would certainly go auto tuner.
I was trying to. This is one other thing too. Your point about power utilization. I think the LDGs actually use latching relays. So once it's tuned, it's not using power to stay tuned.
I think it depends on the model. I know all the Elecraft tuners use latching relays, which is one of the things that really attracted me to Elecraft when they've started up. I thought, wow, that's just an obvious, brilliant thing to do, and really nice design technique. Even though it's more expensive, it's really a desirable way to go from a power consumption perspective.
Well, and looking at my AT100 Pro 2, it also uses latching relays. So,
does it?
Yeah. Go auto.
Yeah, go auto. All right, what's the next question?
Next question is Rick KA0EGL writes, I'm stuck in a limited space situation. Currently, I put up a bent dipole on my upstairs wall for 20 meters. According to the reports I've gotten, it seems to work great. In an effort to reduce the number of coax feeds running around the room, I'm thinking about attaching dipoles for 15 and 10 meters to the same balun and feeding them through the same coax and let the resonance select the proper set of wires for transmission. I'm wondering how much interaction there would be between the dipoles, as I want to get the most bang for the buck, yet don't want to detract from the 20-meter dipole's performance very much. I was planning to try to simulate in a 4NEC 2X, which I'm assuming is a antenna modeling application, but I haven't figured out yet how to do it. Yeah, and NEC antenna modeling stuff is hard. Do you have any experience with this type of setup?
Well, the interesting thing about his question is early on he said something about upstairs wall. Does that mean it's inside the house or outside the house?
Oh, I the way I read this is that it's totally inside the house.
Yeah, well, I think you have other problems if you're putting your fan dipole inside the house. But okay, let's pretend like it's outside, which would be much better. But anyway, yeah, there are some things to consider. So when you do a fan dipole, the elements can interact. So it's unlike a single band dipole where you're tuning the dipole for a particular frequency. The fan dipole, you have to do that, but varying the length of one band element and also the distance between the elements will have some interaction there. So yeah, it's a little bit trickier to tune. So for instance, if you have a fan dipole, you've got, let's say, 3 dipoles at one center feed point. You'll see the commercial ones have fixed insulators that spread the wire elements apart from one another. And if that spread distance changes, the angle between the wire elements change, you can change the tuning. So even if you don't change the length, the distance between the wire elements will change the tuning. So it's a finickier antenna to tune. And you also have to be careful not to have bands which are an odd harmonic. Like, for example, if you said, well, I want 15, 20, and 40 meters, the 15 and 40 meter elements will both have a low impedance. And so it's not going to work right. So you don't want a 15 and a 40 on the same multiband dipole. So you have to kind of think about what bands you're going to use.
Well, there you go.
So, I mean, kind of the long story short is a fan dipole works fine, but the tuning's a little bit finicky, and you want to make sure that when you construct it, that the fan shape doesn't change after you've built it and tuned it and it's in place.
So I know he said he wanted to use the same balun for all of these, but some other ideas that I would consider is build your fan dipole, but try to figure out a way of using quick disconnect, like banana plugs or something, to the antenna elements, so you can electrically separate them. And it's still, you can leave the elements up, but you don't have to worry about this interaction, because you would just unplug the elements you're not using at the time. Do you think that would work?
Well, of course it would work. It's just, but if the fan dipole feed point is above the roof of the house, you're never going to do that. Maybe if it's in your
I believe this is
house.
in his shack on a second story interior wall in a bedroom.
Yeah, if you could reach up and get to the feed point, I guess you could certainly do that. But the whole theory of how a fan dipole works is if I have, let's say, a 20 and a 40 meter dipole hooked up to the same feed point, when the radio is on, let's say, 20 meters, it sees a low impedance on the wires that are cut at a quarter wave each on 20. And it sees a very high impedance on the 40 meter wires. Remember from previous conversations, a half wave end-fed wire is the highest impedance point you can have. So when the energy goes to the feed point on 20 meters, it'll see low impedance on 20 and high impedance on the 40 meter wire. And essentially the 40 meter wire looks disconnected from the circuit, which is why it works. So that's, there's no reason to disconnect it. I mean, you could, but you don't really have to. And it's also the reason, by the way, why it's a problem if you have a third harmonic like 40 and 15, because the 40 meter dipole will look like a low impedance on 40 meters, and a 15 meter signal on the 40 meter dipole will also look like a fairly low impedance because it's the third harmonic. So if you had multiple bands, just make sure you don't have a third harmonic relationship between any two bands, and you're probably fine.
All right. Well, that's going to be it for questions this week and for the episode in general. So the antenna analyzer kit is almost all but done. Got a couple of other exciting things brewing in the background, which we will reveal as they become available. In the meantime, please continue sending us your questions, comments, critical feedback, praise, funny stories, and pictures. You can find me on Twitter at KF7IJZ, and you can reach me via email, jeremy@hamradio360.com.
And I'm at KJ6VU on Twitter, and George at hamradio360.com.
And remember, don't forget, you can save 5% with the code RADIO5 with our sponsor, MCM Electronics, for all of your component, hobby board, tool, and any other needs to equip your workbench. That's mcmelectronics.com. Save 5% with the code RADIO5.
73, everybody.
73.
WWV. All the time, all the time. Same time, same station, every time. WWV. 1, 2, 3, 4. Every second counts at WWV. For a good time, call 555-4-WWV. WWV, for the time of your life. We'll be back with the time on WWV in just a minute. But first, here's another minute.